Hello everyone. So today we will be going over a brief overview of the different machine learning tools we can use to approach different types of problems. I am attempting to construct a mind map of a very general overview on how we can find the best estimator for our job. Many times, the hardest machine learning problem can be actually finding the right estimator for the job. Different estimators are better suited for different types of data and different problems, so it is critical that we find the right estimator. In order to make this a bit easier and clearer hopefully, I have built a small mind map which should give you a rough guide on how to approach different problems. This is a very general overview and I will not be going into any mathematical detail. The aim of this video is to give you a general idea of how different problems can be solved and not go into detail about each estimator. So, starting from here, the first thing we need to ask ourselves is, do we have more than 50 samples of data? If not, then this is a dead end. We simply need to get more data. There's not much you can do from here. So let's assume that we have more than 50 samples. So do we have more than 50 samples? Yes. Are we going to predict a category? So let's say we are going to predict a category, then yes. But you might ask, why is this important? The reason is that we can actually predict other things, not just categories, like are we going to predict a quantity? Or maybe we are just simply looking at the data and hoping to reduce the dimensionality of the data sets. So after we have confirmed that we have more than 50 samples of data, we are asking if we are going to predict a category. If so, then we should ask if we have labeled data or not. So if we know that we need to predict a category, the next logical question is to ask ourselves, do we have labeled data? Now, starting from yes, we do have labeled data, then this is going to be a classification problem. And what classification is, it's fundamentally trying to identify to which of a set of categories a new observation belongs on the basis of a training set of data containing observations whose category membership is already known. So that is classification, and classification occurs if we do have labeled data. Now, assuming that we do have labeled data, we have to ask ourselves further, do we have less than 100,000 samples? If we have less than 100,000 samples, then yes, we do have fewer samples. Then we can perform linear SVC. Now, linear SVC, or linear support vector classification, is basically capable of performing multi-class classification on a dataset. This may actually be used with different kernel types. So we will be seeing SVC further on as well, and basically SVC can be used with different kernel types. So if you see somewhere else SVC in this mind map, then you should assume that it uses a different kernel type than the previous SVC in other areas. So if we have less than 100,000 samples and we have used linear SVC and it is not working, we can further ask ourselves, is our data text? Do we have text data? If the answer is yes, we can go on to perform naive Bayes method, which is a set of supervised learning algorithms based on applying Bayes' theorem with the naive assumption. So this type of classifier can be extremely fast compared to more sophisticated methods. And even though it is a decent classifier, it is known to be a bad estimator. However, that in our case will not be such an issue because we are after classification. This is a classification type of problem. So we can use the naive Bayes method if the data is text. If we do not have text data, then we can go on to perform k-neighbors classifier. Now what this does, this is a type of instance-based learning. So it does not attempt to construct a general internal model, but simply stores instances of the data. So if k-neighbors classifier is not working in this case, we can also try to go on to a different method, which is SVC or ensemble classifiers. Now, this is a similar method, but accepts slightly different sets of parameters and has different mathematical formulation, so it might work in this case. And as you know, we have seen SVC before, but these use different kernel methods. I will not be going into that later, but kernel methods can include linear kernel, RBF kernel, polynomial kernels. So this is just a brief general overview that SVC with different kernel types can be used here and here. Next, what happens if we do not have less than 100,000 samples, but we actually have more than 100,000 samples? So we can then use SGD classifier, which is basically a stochastic gradient descent learning routine. This supports different loss functions and penalties for classification. So we can try that. If this does not work, then we can go for a kernel approximation method. That's the next logical route we can take if we have more than 100,000 samples. Next. So we have more than 50 samples of data. Yes, we are going to predict a category. If we do not have labeled data, then this is a clustering problem, most likely. What do I mean when I say clustering problem? So clustering is the task of grouping a set of objects in such a way that in the same group, which are called clusters, they are more similar in some sense to each other than the ones in different groups or different clusters. Now, the first step, the first question we need to ask ourselves is the number of categories known? And this can either be yes, we do know the number of categories, or no. Either of these, whether we do know the number of categories or we do not know the number of categories, we always need to ask ourselves in this case, do we have less than 10,000 samples? So let's say we do have labeled data classification. So now let's say we do not have labeled data and we know the number of categories. So we are here. Do we have less than 10,000 samples? Yes, we have less than 10,000 samples. So we can try the k-means algorithm. The k-means algorithm works by clustering data and trying to separate samples in n groups of equal variance. This minimizes a criterion known as the inertia. Often, k-means is referred to as Lloyd's algorithm, so you may have heard of that instead. What happens if k-means does not work? We have another option. We can try spectral clustering. Spectral clustering, this basically is a procedure done before k-means. So if k-means by itself does not work, we can perform spectral clustering and then still perform k-means. So this procedure is done before the k-means, as I have said, but k-means is still performed after. So these are not separate, but if k-means alone does not work, then we can proceed to try spectral clustering beforehand. What happens if we do not have less than 10k samples? So we have more than 10k samples, then mini-batch k-means should probably work. Mini-batch k-means is a variant of the k-means algorithm which uses mini-batches. The use of mini-batches reduces the computation time, so that makes sense that if we have more than 10k samples, we use mini-batches. So that's about it. Now, what happens if we do not know the number of categories in our cluster? So do we still have less than 10,000 samples? Yes, we do have few samples, so we can try out the mean shift method. So mean shift clustering aims to discover blobs in a smooth density of samples. That's the main task for mean shift. Now, if we do not have labeled data and we do not know the number of categories and we have more than 10,000 samples, so this is the part we're down, then it's tough luck. There are no methods, there are no simple methods, I should say, so we won't be going into that. So this, if you're in this area, then you probably need something more complex. Next. So we've gone down when we are predicting a category. We have seen all the estimators we can use when we are predicting a category. By the way, the ones in blue are estimators, and the ones in the other color are simply questions we need to ask ourselves. So we may ask, what are we trying to predict if it's not a category? So if we are not predicting a category, so here, then we might be predicting a quantity. So let's say yes, we are predicting a quantity. If we are predicting a quantity, then we are going into what is called a regression type of problem, regression solving. So regression has a far broader purpose and scope than simply classification or machine learning. And a generic regression method which you might be familiar with is the gradient descent method, which is an algorithm capable of finding optimal solutions to a wide range of problems. The general idea of gradient descent is to tweak parameters iteratively in order to minimize the cost function. So if we are predicting a quantity, then we most likely are performing some kind of regression. We need to ask ourselves now, do we have less than 100k samples? If we don't have less than 100k samples, so we actually have more than 100,000 samples, we can use or opt for the SGD regressor. This is a plain stochastic gradient descent learning routine. So it is suited for problems with a large number of training samples, greater than 100k in this case. For other problems which are fewer than 100,000 samples, so yes, we can use different methods. Now, we can ask ourselves, are few features important? So few features should be important, or are there more than a few features which are important? Are we interested in more features? If the answer is yes, then few features are important. We can proceed to a lasso or elastic net methods. Now, what these are basically, these are both used when there is a small sample size, and they tend to prefer solutions with fewer parameter values. So that's why we are in this yes branch here. Now, if more than a few features should be important, we cannot use lasso or elastic net since they prefer fewer parameter values. We can use ridge regression or SVR. Now, ridge regression or SVR stands for support vector classification. These can be extended to solve regression problems as well. If this does not work, this regression or SVR do not work, we can try out ensemble regressors /SVR or SVR. So the goal of the ensemble methods is basically to combine the prediction of several Bayes estimators, so within a given learning algorithm. This increases robustness. Next. So we have seen here what happens when we need to predict a quantity. Yes, we do. Yes, we have less than 100,000 samples, and we have seen just now ensemble regressors. We have more than a few features should be important. So that is the path we took. Next, what happens if we have more than 50 samples of data? We do not want to predict a category, and we do not want to predict a quantity. So dimensionality reduction is the only area we have left to explore. Now, we have to ask ourselves, what are we doing if we do not want to predict a quantity? Are we just looking at the data? So if we are not just looking at the data and we want to predict a structure, this is not going to be simple, and I won't be going over it in this video. So tough luck once again. Now, if we are just looking at the data, we might be interested in reducing the dimensionality of the data set. So if yes, we are just looking, we may try out a method known as randomized PCA. Now, PCA is used to decompose a multivariate data set, and however, this may not always work. So if this does not work, we need to evaluate the sample size we have. So if we have less than 10,000 samples, So yes, we do have fewer. We may try out isomap or spectral embedding, which I won't be going into, but these are one of the earliest approaches to manifold learning. And if this does not work, we may go into LLE, a method known as LLE. And if we have more than 10,000 samples, we may use a kernel approximation method. So we have seen something similar to that. So yes, if we are not predicting a category and we are not predicting a quantity, then we are most likely interested in dimensionality reduction. If you guys don't know what that is, it's basically the process of reducing the number of random variables by obtaining a set of principal variables. So that is a very general overview of some of the methods available to us. And now this is the full picture. I can actually post this in the comments below. If you have any questions, feel free to ask, and hope you found it useful. Thank you.